Okay, let's get back to the problem at hand here. So remember, we had a north pole, we had a south pole, we have magnetic field, which is homogeneous between the poles. And what we're going to do is we're going to take a charged entity here, and we're going to fire it into the magnetic field such that V vector is perpendicular to the magnetic field vector. Okay. Now we're going to reorient this. So let's rotate this by 90 degrees. Okay, and so what we're going to have then is we're going to have our magnetic field pointing into the plane of the paper. So this vector designation is quite common in physics whenever we're dealing with 3 dimensions. So if we have a circle with a little dot in it, it means that this is a vector. It's a vector coming out of the plane of the paper. And with a little cross inside that circle, this is a vector going into the plane of the paper. So we're going to need this designation throughout our discussion here. So this then is going to be magnetic field into the plane of the paper. And so the north pole is going to be above the plane of the paper, and the south pole will be behind the paper, right, on a plane behind the paper. And again, we're going to be shooting our charged entity into this magnetic field. And again, V is perpendicular to the magnetic field. Now, you have to appreciate that really what we're after here. What is it that we're after? We're after the force law of charges in magnetic fields. That's what we're after, right? So what does the force law look like? Okay. And so this is strictly by experiment, right? This is not grounded in any more primal theory. So, right, so this is going to be completely grounded in experiment, much like what we're doing here on paper. We're doing sort of thought experiments, grounded in experiment. And so what was noticed here is that as this charge entered the magnetic field, what happened is that it traced out a circular path. Okay. Now that's rather interesting, okay, because if we go back and look at our previous problems in gravitational fields and electric fields, and again, let's just quickly review that, okay? Because I think this is important enough to go back and review that. So if we were to imagine again, paradigm 1, If you remember that from first semester, right? Paradigm 1. If we were to go back and throw a ball or shoot a ball off a step into a gravitational field, great, I'll try to maintain the same colors here. So here's some mass, and we're shooting it into this gravitational field. This could very well be a step, right? Remember paradigm 1, for those of you who were with me first semester. This is some V0x. We all know, or hopefully we all know, what the resulting trajectory would be, right? It would be a parabolic trajectory. Okay, this would be a parabolic trajectory. Parabolic trajectory, and we studied that in grand detail. And likewise, if we were to take a parallel plate arrangement of charge, again, with the electric field now oriented like so, from positive plate to negative plate. Again, the electric field is constant and homogeneous. And if we were to take a positive charge and shoot it into that electric field, then the mathematics is identical. The resulting trajectory would be completely analogous to projectile motion, and this would be a parabolic trajectory. Okay, so and again, these are mathematically identical. One should be able to go back and analyze the two-dimensional kinematics of each of these problems. Okay, and again, this especially for shooting charges into electric fields, that might be good fodder for final exam material, right? So again, going back to this problem, we shoot a charged particle into a magnetic field, and we get a circular trajectory. Now let's redraw that, because that's important enough to redraw down here. So again, we have our magnetic field into the plane of the paper. Like so. So this is B into the plane of the paper. We shoot our positively charged particle into this magnetic field with some velocity v, and experimentally we determine that it traces out a circular trajectory, right? So this is a circular trajectory, and it has a radius of r, and most importantly, or as important, the velocity magnitude doesn't change. So the magnitude of the velocity is constant. Now, we've encountered problems before where the magnitude of the velocity is constant, right? So this is going to imply uniform circular motion. And that's going to imply that as this charged entity moves around this circular path, that it's going to experience a center-seeking acceleration. So all around this circular path is going to be a center-seeking or radial or centripetal acceleration. Now, that implies, right, so A is radial, right, because it's along a radii toward the center of the circle, or centripetal acceleration. Right, that implies a force, right? That implies a force also directed toward the center of the circle. And for the first time, we actually got an effect by the magnetic field. Okay, so the magnetic field now exerts a force on the moving charge. This time when the velocity vector is perpendicular to the magnetic field vector. So we're beginning to understand a little bit more about this problem. Now again, if you were to vary the charge, keeping the magnetic field strength constant, vary the velocity, magnitude of the velocity, keeping the charge and the magnetic field constant, right? So we can do a whole host of experiments here. One would come to the conclusion that the magnetic force is linearly related to the charge of the magnitude of the charge of the charged entity. It's directly proportional to or linearly related to the magnitude of the velocity. And it is linearly related to the magnitude of the magnetic field. Okay? But that still doesn't explain the experiment between shooting the charged particle in parallel or perpendicular to the magnetic field. Now let's keep this in mind, right? So we get no effect when the velocity vector is parallel to the magnetic field vector, and we get a significant effect, or I should say, because we've done the experiment, a maximal effect when the velocity vector is perpendicular to the magnetic field. So I smell a trigonometric function. What trigonometric function is 0 when two vectors have a 0 angle between them, and maximum when the angle between the two vectors is 90 degrees. Right? So I smell a sine function, and so the magnetic force now in magnitude is proportional to Q VB times the sine of theta. How do we change proportionalities to equalities? Well, through a multiplicative constant. So for the electrostatic force, that was 1 over 4 pi epsilon naught. Nicely here, right? The constant of proportionality is just 1. And so we have that the magnitude of the magnetic force is equal to the magnitude of the charge times the magnitude of the velocity times the magnitude of the magnetic field strength times the sine of the smallest angle between the velocity vector and the magnetic field vector. So we should write these down, right? So this is the magnitude of the magnetic force, which we've given as F subscript B. This is the magnitude of the charge. This is the magnitude of the velocity. Got all kinds of things going on here. Magnitude of the velocity. This is the magnitude magnitude of the magnetic field, and theta is the smallest angle between the velocity vector and the magnetic field vector. Okay? So this is a good time to discuss units on the magnetic field, and then we'll call this piece of the lecture done, and then we'll go back and look at some more nuance of the magnetic field. So we know that that forces are in units of newtons, that charge is in units of coulombs, that the magnitude of the velocity is in units of meters per second. And then whatever the units of B are going to be, we need to figure out. And sine of theta has no units, that's unitless. So whatever the units of magnetic field are, right, they're going to be equal to Newton seconds per coulomb meter. Right, Newton seconds per coulomb meter. Now, that's quite a bit to carry around. And so we renamed that, we defined that to be the Tesla, capital T. Okay? So the units on the magnetic field are in units of the Tesla, capital T. And just to ground you in that unit, the magnetic field of the Earth is on the order of 1 times 10 to the negative 4 Tesla. If you were to actually go into an MRI, the magnetic fields for those could be 3 to 10 Tesla. So they're very strong magnetic fields. Another unit of magnetic field is commonly used in many areas of physics and chemistry, and it's actually its staying power has has persisted, and so it's the Gauss. It's the unit of the Gauss, capital G, and there are 1 times 10 to the 4 Gauss in 1 Tesla. Okay, so that's a good conversion to be acquainted with. So let's end right there, and I'll upload this, and then we'll get back and we'll add some more, as I said, some more nuance to the magnetic force. Okay, thanks, guys.